this talk is based on this work with collaborators Teen and Thomas from Aarhus University, Denmark. So, as we know, we have three neutrinos in the mass eigenstates, and these are quantum superpositions of neutrinos in the flavored eigenstate. And cosmology gives very strong bounds on the sum of neutrino masses from cosmology. And in the late universe, the neutrino energy density depends on this sum of neutrino masses. And also we have the radiation density in the early universe, which depends on the effective number of relativistic degrees of freedom. For this purpose, for the purpose of this talk, you can consider it to be the number of neutrinos. And in this case, we also use this approximation of degenerate hierarchy where all the masses are the same. This is technically the lambda CDM parameterization, which has 6 parameters. Omega C and omega B are the present day physical CDM and baryon densities. Eta MC is the parameter for the angular size of the sound horizon, which is the ratio between the sound horizon and the angular diameter distance at photon decoupling. Tau is the optical depth to reionization, and NS and AS are the power law, spectral index, and amplitude of the primordial curvature perturbations. So this is the form of the past spectrum that we are considering. So I will talk about neutrino self-interactions mediated by a heavy scalar. It is exactly same as what Mansi had talked previously yesterday. And so in this paper, we have updated the constraints from cosmology on neutrino self-interactions mediated by a heavy scalar. The mass is taken to be greater than 1 keV for CMB perturbations. The perturbations probed by CMB, because CMB temperature is 0.26 CV at the time of decoupling, so which is far lower than this keV range. And we use a simplified interaction term like this, where we consider two interacting scenarios. One is the 3 neutrino interacting scenario, where we take the form to be diagonal, and we also consider a 1 neutrino interacting case, where we take this delta kk term to be either with the k representing either 1, 2, or 3. So in this case, only one mass eigenstate is interacting, but technically we want it in the flavor eigenstate, because as you know from particle physics experiments, basically the neutrino interactions in only the tau neutrinos are allowed currently. So this is the more realistic case to consider from cosmological perspective and from particle physics perspective. This is the effective self-coupling. So, and if G effective is greater than G Fermi, then even after the weak interaction becomes the weak interaction rate becomes less than the Hubble expansion rate when T is around 1 mega electron volts, when the neutrinos basically decouple from the photons. But if G effective is greater than G Fermi, then these neutrinos will remain interacting with each other even after this decoupling happens. So they will continue self-interacting with each other, which will sort of suppress their anisotropic stress. And if it is in only one neutrino, then it will suppress the anisotropic stress only in that particular neutrino. And then you can calculate the self-interaction rate per particle, which is G effective squared T nu to the power 5. And then neutrinos don't free stream unless this interaction rate becomes smaller than the Hubble parameter. So this is basically the Feynman diagram of the interaction. So, and for temperatures which are much smaller than M, this becomes effective 4 fermion interaction. So there is no need for it to be a scalar particle. It can be a vector boson as well, and all our analysis results will also correspond to that as well. So ultimately, you just need an effective 4 fermion interaction. So now to briefly summarize inflationary models, single field inflationary models, we have this scalar power spectrum as well as power spectrum for tensor perturbations. And then you can define this tensor to scalar ratio R as AT divided by AS. And we consider this pivot scale of K star, which is 0.05 H MPC inverse. And a general slow roll single field inflationary model will have this potential V phi. And then you can define the slow roll parameters epsilon and eta. And then you can define the cosmological observables based on these slow roll parameters. Now, inflation conventionally ends when one of these parameters, either eta or epsilon, becomes 1. In this case, we take epsilon to be equal to 1. And then you can define the number of e-foldings before inflation ends, and that is n star. Now, for observable fluctuations in CMB, you need to take n star to be around 50 to 60, and we take this variation in n star. And so given a potential V phi and a choice of n star, you can predict the scalar spectral index and also the tensor to scalar ratio for any single field inflationary model. So we are particularly interested in these two inflationary models, natural inflation, which has a potential of V and I, and Coleman-Weinberg inflation, which has a potential of this. There are some model parameters here, but effectively what we are considering here is that both of these models are basically ruled out at more than 2 sigma in the lambda CDM plus R model, where you consider tensor perturbations as well. So, but our cosmological model of interest is this 10-parameter model, which has this log G effective parameter as well as N effective and sum of neutron masses, and also this tensor to scalar ratio. And so basically we modify the Boltzmann equations in both scalar and tensor perturbations. And as I said, we consider 2 scenarios, 3 neutrino interacting and 1 neutrino interacting. So these are cosmological Boltzmann equations. So since neutrinos are collisional, you have to, so these are in the synchronous gauge. And so we start with the perturbed metric, and then you can define this H and eta, these two parameters, these are sort of similar to the co-moving Newtonian gauge where you have phi and psi, but this is in a different gauge. And I'll skip to that completely to this part where you have this expansion, and basically for multipoles 2 and higher, the neutrino interactions will give you a damping term in the equations, but the first 2 equations are unaffected because of energy and momentum conservation in the interactions, but all the other terms in the hierarchy of this Boltzmann hierarchy will be affected by these damping terms, and this depends on this A multiplied by this gamma, which is the interaction rate, and alpha L are some model dependent coefficients of order unity, and that depends on this particular scalar field model that we have taken. Sorry, scalar interaction model that we have taken. Now, as I said, our cosmological model of interest is this, and when we calculate the posterior distributions, then log G effective, we take a very broad prior and log G effective, but you can divide this in 2 modes, which is moderately interacting mode and the strongly interacting mode. So the posterior is basically bimodal, and to compare it with the non-interacting case, we also take a situation where the G effective is 0. So to show you how disfavored this is by cosmological data currently in the lambda CDM model, you can see this magenta curves are for the predictions for natural inflation, and this black line that you see is the prediction for Coleman-Weinberg inflation. So basically, this has a vanishingly small r, and as you can see, both of these are disfavored at more than 2 sigma in the lambda CDM plus R model. And if you take non-interacting, if you take the non-interacting case, even then they are disfavored at more than 2 sigma for the most constraining data set, which is Planck 2018 plus Bicep-Cake 2018, and some extra data, which is Planck 2018 lensing plus BAO plus redshift space distortions and uncalibrated supernova data. And so even then, they are disfavored at more than 2 sigma. But when we consider the 3 neutrino interacting model or 1 neutrino interacting model, then they become there is some parameter space which is included within the 2 sigma. So this is the main result of our paper, that you see this, that these become viable models when we consider neutrino self-interactions. And this happens because these self-interactions lower the value of the scalar spectral index from the lambda CDM model. So in the log G effective posterior distribution, you see these kind of bumps. In the 3 neutrino interacting model, these 2 modes are completely separated. This is the moderately interacting mode. This is the strongly interacting mode. But in case of 1 neutrino interacting model, these are not fully separated and they kind of overlap. But and the thing is that this 3 neutrino interacting model, where you have the strongly interacting mode, this is actually disfavored by the data. But all the other modes, this moderately interacting mode or both the strongly interacting mode or moderately interacting mode, these are actually not disfavored by the data. So these provide fits quite similar to lambda CDM. So as far as cosmological data is concerned, except the strongly interacting mode in all 3 neutrinos, the other modes are kind of viable right now. So if we split the modes, then you can see again that as far as the cosmologically viable posterior distributions are concerned in the 2D contour plots or for R and NS, you can see that these models are still valid at 2 sigma. So if you have, so to summarize that, so neutrino self-interactions induce changes in the CMB spectra, which cause lower values of NS. And in this analysis, we include the neutrino interaction in both scalar and tensor perturbation equations. We consider 2 scenarios where 3 neutrinos are interacting and 1 neutrino is interacting. And we find that for full range runs of log G effective, both this natural inflation and Coleman-Weinberg inflation are allowed at 2 sigma, though not at 1 sigma. And the strongest bounds from particle physics experiments currently only allow the 1 neutrino interacting, moderately interacting mode. But even then, both these inflationary models are still allowed at 2 sigma, even with the most constraining dataset combination. Thank you.
Okay, thank you, Shobhit, for a nice talk.